So I want you to imagine for a second that you hire, like this brilliant chef, to cook a massive 5-course meal.
Okay, I'm tracking with you.
Right. But there's a catch. Every time they put something in the oven and they step back to wait for it to bake,
Yeah.
they completely wipe their own memory.
Like a total reset.
Exactly.
Mhm.
A total factory reset. So when the timer goes off, they have to relearn how to cook from scratch.
Oh, wow.
Yeah, they have to reread the entire recipe, figure out what they were even doing, just to take the pan out of the oven.
Which sounds completely insane.
It sounds totally insane.
Yeah.
But right now, today, that is exactly how our multi-million-dollar AI data centers are treating autonomous AI agents.
Yeah, and I mean, if you've been following the AI space lately, you know we really aren't just talking to simple chatbots anymore.
Right.
We're deploying these autonomous agents to, write software features or debug whole systems or just browse the web on their own. But the infrastructure running them is totally stuck in the past.
And that actually brings us to the mission of our deep dive today. We're unpacking this crazy 2026 state-of-the-art paper. It's called SAGA, Workflow Atomic Scheduling for AI Agent Inference on GPU Clusters.
Quite the mouthful.
It really is. But our goal here is to basically understand why our current AI plumbing, the infrastructure, is fundamentally broken for these new agent workflows.
Yeah.
And more importantly, how SAGA proposes this radical shift in scheduling GPU's graphics processing units to finally fix it.
Because to really grasp the scale of this, you have to look at platforms like GitHub Copilot Workspace or Amazon Q Developer.
Our big ones.
Exactly. They are routing millions of these agent tasks through these massive shared GPU clusters every single day.
Millions.
Millions. But there's this hidden inefficiency that is just causing a massive bottleneck.
So what's the actual conflict here?
Well, the core conflict is that we are trying to run continuous, complex, long-running AI programs on infrastructure that was, frankly, hard-coded for one-off chat requests.
So it's like using a toaster to try and roast a whole turkey.
Basically, yeah.
Okay, so let's get into the actual mechanics of that mismatch. Why exactly are these highly advanced systems giving our AI agents what amounts to like goldfish memory?
So it really comes down to the fundamental difference in the loop.
Oh.
Unlike a single prompt where, you ask a question, you get an answer, an agent executes what researchers call a thought-action-observation loop.
Thought-action-observation.
Right. To complete just a single user request, an agent might make 10 to 100 chained language model calls.
Wow.
Yeah, because it has to interleave its internal reasoning with the use of external tools.
Like what kind of tools?
So it thinks, right. Then it pauses to run a Python script. It observes the terminal output, maybe it reads a local file, pings a web API, and then it thinks again based on that new data.
So every single step is entirely contingent on the context of the previous step.
Exactly.
It's just building this massive internal context window as it goes.
And that context has a very real physical weight in the data center.
How heavy are we talking?
Well, the paper highlights this staggering data point.
Yeah.
If you're using a 70 billion parameter model like, say, Llama 370B with a 32,000 token context window, the system generates about 10.7 gigabytes of what we call KV cache per session.
Okay, wait. Let's slow down and explain that for a second for everyone listening. We hear this term KV cache or key value cache thrown around a lot.
Yeah, constantly.
What is actually taking up 10.7 gigabytes of space? Because that's the size of a high-definition movie.
It's massive. So the KV cache is essentially the mathematical representation of the AI's memory of the current task.
Okay.
When a language model processes text, it calculates these attention states, which is basically how every single word relates to every other word in the sequence.
Right.
Now, instead of recalculating those insanely complex mathematical relationships every single time the agent generates a new word, the system stores those intermediate calculations.
Just to save time.
Exactly. It stores them as large matrices in the GPU's memory. That is the KV cache.
Oh, I see.
So the model needs that 10.7 gigabytes of data instantly accessible in the ultra-fast GPU memory just to generate the very next step in its thought process.
Which brings us right back to our chef wiping their memory. When the agent pauses to use a tool, say he needs to compile some code, what is the system actually doing with that 10.7 gigabytes?
Well, it throws it in the trash.
Literally just trashes it.
Trashes it. Current schedulers, like the widely used VLLM system, they were built for chatbots. They assume requests are memoryless and independent.
Because humans are slow.
Right. When a human is chatting with an AI, the AI answers, and then the human takes, maybe 30 seconds to read the answer and type a response.
And 30 seconds is an eternity for a GPU.
Exactly. During that human delay, the GPU scheduler looks at the idle time and evicts the 10 GB memory to free up space for another user's query.
Which makes sense for chat.
It makes total sense for chat. But an agent isn't a human typing slowly.
No.
An agent is pausing to run a tool for maybe half a second. Yeah, so when the tool finishes and the agent needs to resume its loop, the memory is just gone.
It was evicted.
Evicted. So the AI has to pull the entire history of the task and mathematically regenerate that entire 10.7 gigabyte KV cache from scratch just to take the next step.
The computational waste there must be just massive. Like every time it runs a basic command line tool, it has to reread the entire history of the project.
It is devastating to performance. So the researchers ran these tests on SWE Bench, which is this rigorous benchmark for software engineering agents.
Right.
They found that current systems spend 38% of their total execution time just regenerating this discarded memory.
38%. That's over a third of the time doing nothing but trying to remember what it was doing.
Exactly. It inflates the end-to-end task completion time by 3 to 8 times.
That is wild.
Right. Imagine a task that should take 1 minute taking 8 minutes, purely because the system just keeps deleting its own notes.
So, okay, if evicting the memory is the root cause of this huge slowdown, the really obvious solution seems to be, don't delete it. Right. Like, why don't we just configure the GPUs to hold on to the KV cache until the agent explicitly says, hey, I'm done with this task?
Well, it all comes down to what we call the variable gap problem.
The variable gap.
Yeah. The wait times for external tools are wildly unpredictable.
Oh, I see.
Like, if an agent runs a local file operation, that might take 45 milliseconds. But if it needs to compile a heavy piece of C++ code, that might take 28 seconds.
Or a web API could take even longer.
Exactly. If it queries a web API, it could hang for 45 seconds or more, depending on, network latency.
And GPU memory is incredibly expensive real estate.
Extremely expensive.
You can't just block off 10 gigabytes of high bandwidth memory for a full minute while a web page loads, especially when there are, hundreds of other users waiting for compute?
Precisely. You just can't. Traditional systems use a strict least recently used, or LRU, eviction policy.
LRU.
Yeah, meaning if memory is idle and the system is crowded, the oldest idle memory gets evicted first. They just don't differentiate between a human taking a coffee break and an agent waiting 50 milliseconds for a database query.
Gotcha. So this is where the source paper introduces SAGA.
Yes.
How does SAGA actually manage to keep the memory alive without unnecessarily hoarding it and, starving all the other users?
So SAGA introduces a massive structural innovation. They call them agent execution graphs, or AEGs.
AEGs.
Yeah. Instead of scheduling single isolated inference requests, SAGA actually surfaces the entire workflow structure to the global scheduler right at the start.
Wow.
It basically maps out the architecture of the agent's mind.
Wait. If the agent is acting autonomously and deciding what to do on the fly, where's this map coming from?
That is the big question.
I mean, the system can't read the AI's mind before it makes a decision. Who is drawing this graph?
So that is the critical distinction here. It doesn't actually need to read the AI's mind because modern agents are built using specific frameworks.
Like LangChain.
Exactly. Like LangChain or Autogen. A developer defines the boundaries of what the agent can actually do.
Oh, so it's not totally unconstrained.
Right. The framework contains defined tools, decision branches, and logical loops. So SAGA intercepts the graph from the framework itself.
Okay, so it says the agent is entering the thought-action-observation loop. Here are the 3 possible tools that it has permission to use, and here are the branches it can take.
Exactly.
So it knows the structure of the labyrinth, even if it doesn't know exactly which turns the AI will take at any given moment.
Perfectly said.
But how does that actually help the scheduler manage the physical memory on the GPU? I mean, it still doesn't know how long a specific API call is going to take, right?
True, but it uses historical data to play the odds. So SAGA implements what they call workflow-aware LRU combined with an adaptive time-to-live, or TTL.
Okay, break that down for me.
Because the scheduler can see what tool the agent just called, thanks to that execution graph, it looks at historical latency distributions for that specific tool across the whole data center.
Oh, that's smart.
Yeah, it calculates a retention time based on the 95th percentile of how long that tool usually takes.
So if it knows the agent just called a database search that usually takes 200 milliseconds, it says, cool, hold the memory.
Yeah.
But what if the prediction is wrong? What if the database hangs and is taking 10 seconds?
So SAGA dynamically scales the retention time based on cluster pressure.
Okay.
If the GPU is sitting at 90% memory utilization, it gets much less generous. It might shrink that holding window significantly.
Sorry, we need the space.
Exactly. And if the timeout hits because the database is hanging, it just evicts the memory just like the old systems.
But I'm guessing that's rare.
Right. Because it has that historical baseline, it avoids premature evictions for the vast majority of normal tool use.
Right.
Furthermore, and this is super cool, SAGA uses that execution graph to speculatively prefetch memory for the most likely next step while the tool is still running.
Oh, wow. So it overlaps the wait time with the preparation time.
Exactly.
So taking our chef analogy from earlier, that's like the sous chef looking at the recipe, realizing the cake is in the oven for exactly 30 minutes, preparing the frosting right at minute 29.
Yes.
So everything is just ready the exact millisecond the timer goes off.
That's a perfect analogy, and the mathematical efficiency of this is remarkable.
I bet.
In the paper's analysis, this method actually brings cache retention to within 1.31 times of Bilottti's optimal offline policy.
Okay, let's clarify Bilottti's optimal policy for everyone listening, because that isn't a real scheduler you can just download and run.
Right. No, definitely not.
It's a theoretical computer science concept.
Right. Bilottti's policy is a theoretical algorithm that has perfect magical knowledge of the future.
Like a crystal ball.
Exactly. You run a trace of all the requests offline, and the algorithm looks ahead to make the absolute perfect eviction choice every single time.
The ultimate benchmark.
Right. It is the mathematical ceiling of perfection. So the fact that SAGA, which is operating in real time with totally unpredictable agents, gets within 1.31 times of that theoretical maximum is huge.
That's incredible.
It really is. By doing this, SAGA slashes the time wasted on regenerating memory from that massive 38% down to just 8%.
Just 8%. That is a massive optimization.
Huge.
Okay, so mapping the workflow basically cures the goldfish memory for a single agent.
Yep.
But we are talking about multi-million-dollar data centers here.
Yeah.
I mean, there aren't just 1 or 2 GPUs in these clusters.
No, we're talking big racks.
Right. There are 64, maybe hundreds of GPUs all working together.
Yes.
So when an agent wakes back up after using a tool, how do you ensure the global network routes that agent back to the exact physical GPU that is currently holding its 10.7 gigabyte memory?
That is the cluster-wide choreography that SAGA has to manage.
Okay.
It uses a concept called session affinity batching.
Yeah.
The global scheduler essentially tags the session. It purposely routes an agent's next request to the exact same GPU worker that currently holds its KV cache.
So it just sticks to one machine.
Right. It strictly prioritizes cache locality.
But wait, doesn't that create a massive bottleneck?
How do you mean?
Well, if I route all the traffic for, like, 5 really heavy agents to server A just because it has their memory, server A is going to be completely overloaded.
Sure.
While, server B right next to it might be sitting completely idle. So you've solved the memory problem, but you've just created a massive traffic jam.
Yeah, you've just identified the classic distributed systems dilemma, affinity versus load balancing.
Right.
You want the compute close to the data, but you also want all your processors working evenly.
Exactly.
So SAGA actually solves this traffic jam with a mechanism called randomized work stealing.
Work stealing. That sounds aggressive. How does a GPU actually steal work from another machine without creating some sort of centralized traffic cop that just slows everything down?
So it uses decentralized randomized polling.
Okay.
If a GPU worker is sitting idle for more than 100 milliseconds, or if it detects that the load imbalance across the cluster has hit a 2.0x ratio.
Meaning one machine is working twice as hard as another.
Exactly. So if it sees that, the idle GPU initiates a steal. It randomly queries a few other GPUs, finds the overloaded one, and literally rips a pending session away from it.
But wait, if it steals the session, doesn't it leave the memory behind?
Well,
Because we literally just spent all this time trying to keep the memory with the agent.
you'd think so, but no. SAGA migrates the memory cache along with the session.
All 10.7 gigabytes of it.
All of it. It uses a live migration protocol over the cluster's InfiniBand network.
Okay, let's explain InfiniBand really quick,
Oh,
because
oh.
that is the secret sauce here. That this isn't your standard Wi-Fi or standard Ethernet.
Oh, absolutely not. InfiniBand is an ultra-high bandwidth networking protocol specifically used in supercomputers and AI clusters.
Right, it's insanely fast.
Yeah, and it allows for remote direct memory access, or RDMA.
RDM.
Right. That means one GPU can directly pull data from the memory of another GPU without having to ask the central CPU to package it up and send it.
It just bypasses the CPU entirely.
Exactly. It's a direct highway. Because of that direct connection, the idle GPU can pull that massive 10.7 gigabyte KV cache over the network in about 230 milliseconds on average.
Wow. So taking, what, a quarter of a second to move the data over the network is still vastly superior to taking potentially several seconds or even minutes to mathematically regenerate it from scratch?
Precisely. It is so much faster. And the data shows this keeps worker utilization perfectly balanced.
Really?
Yeah, without work stealing, you see a wild spread where some GPUs are sitting at 23% utilization and others are totally slammed at 94%.
Just a man.
A total mess. But with SAGA, that narrows to a really tight 68% to 79% utilization range across the board.
It's super consistent.
Very consistent. And even with the slight overhead of moving that memory around, it still completes tasks 1.64 times faster than current state-of-the-art schedulers.
Okay, so the system is predicting the memory needs, it's holding on to it when it should, and it is perfectly balancing the hardware.
Yeah.
But what about the humans, waiting on the other side of the screen?
The tricky part.
Right, because you have hundreds of different tenants using this cluster at the same time.
Yeah.
Some of them are just asking an agent to write, like a single regex function.
Right, okay.
And others are asking an agent to refactor an entire massive code base.
Exactly.
How does SAGA prioritize who goes first?
So this requires completely redefining what fairness means in an AI data center.
Okay.
Traditional systems, like VLLM, prioritize what we call throughput, which is the raw volume of work.
Okay, just getting stuff done.
Right. Their goal is to churn out as many individual tokens as possible per second.
They want the highest aggregate score, basically.
Yes. But for an agent workflow, throughput is actually a really deceptive metric.
Why is that?
Let's say your agent needs to execute 100 sequential steps to refactor that code base you mentioned.
Okay.
If the scheduler pushes 99 of those steps through at lightning speed, but then deprioritizes the very last step for 10 minutes because it's focusing on other users.
Oh, I see.
Right. From your perspective, sitting at your desk, the task is still 0% done.
Because you can't use 99% of a refactored code base. It's either done or it's not.
Exactly.
Yeah.
It's totally useless until it's finished.
So we are kind of moving from like a bakery line where you take a ticket and everyone gets served one pastry at a time, regardless of how big their total order is,
Right.
to something more like an emergency room triage,
All right.
where the system actively calculates who needs to be pushed through right now to finish their specific procedure.
That is an excellent way to visualize it. So SAGA introduces a metric called Agent Fair Share, or AFS.
AFS, yeah.
Yes, it schedules based entirely on expected task completion time rather than individual request throughput.
So it looks at the finish line.
Exactly. Tenants with more urgent remaining work relative to their deadlines get higher priority.
Because it knows the workflow.
Right. Because SAGA can see the agent execution graph, it calculates exactly how many GPU seconds are needed to finish the remaining nodes for a specific user and allocates cluster capacity proportionally.
Okay, but how do they prevent the massive tasks from just bulldozing the small ones?
Yeah.
Because if I just want a 2-second fix, how does the system ensure I don't get totally starved out by the heavy users running those 100-step loops?
So they enforce this using a really fascinating mathematical framework called Lyapunov drift analysis.
Okay, wait, let's break that down, because Lyapunov drift sounds like a concept from orbital mechanics, not data center management.
I know, it sounds super intense.
How does the math actually assign priority?
So it is actually rooted in physics. It deals with the stability of dynamic systems.
Okay.
In SAGA, Lyapunov drift acts as a sort of pressure equalizer. The scheduler assigns a penalty weight to each user's queue.
A penalty weight.
Yeah, and this weight is calculated by multiplying two forces: how much work you have left and how close you are to missing your service deadline.
Oh, I see where this is going.
Right, so if a light user is getting starved by heavy users, their deadline urgency increases.
Because they're waiting too long.
Exactly. And as that urgency rises, their mathematical weight in the scheduler's equation gets heavier and heavier.
So it creates this sort of gravitational pull. The further behind you fall, the harder the system works to pull you to the front of the line.
Exactly. The math guarantees a self-correcting drift toward equilibrium.
That's brilliant.
It is. The system fundamentally cannot ignore a user because eventually their penalty weight will become so massive that the scheduler is mathematically forced to give them GPU cycles.
So it's literally impossible to get permanently stuck.
Right. And the real-world results of this pressure system are incredibly validating.
So what actually happened when they tested this against real production traffic?
Okay, so the researchers ran a workload mimicking real traffic with a mix of heavy, medium, and light users.
Right.
Under the traditional scheduling systems, they only met task deadlines for the light users 43.2% of the time.
Less than half.
Less than half. The small tasks were just getting trapped behind the massive fragmented requests of the heavy users.
So a 43.2% success rate means you are essentially flipping a coin on whether your AI agent actually finishes a simple task on time.
Pretty much.
That is terrible for user experience. I'd be so frustrated.
It's awful. But with Saga's agent fair share, the light users met their deadlines 98.7% of the time.
98.7%.
Yeah. And overall, across all users, heavy, medium, and light Saga hit a 99.2% service level objective attainment.
Wow.
It practically eliminated the starvation of small tasks while keeping the massive tasks right on schedule.
Okay, those numbers are absolutely staggering.
They are.
But, there is always a catch in computer science.
Always a trade-off.
Every architectural choice has a cost. So what is the trade-off for implementing predictive graphs and work stealing and Lyapunov drift? What are we giving up here?
Well, to their credit, the paper is remarkably transparent about this trade-off. Saga trades about 30% of peak throughput to achieve this massive reduction in end-to-end task latency.
30%? I mean, giving up 30% of the raw tokens your data center can produce per minute is a massive pill to swallow for cloud providers.
It is a really significant sacrifice, which means Saga is not a universal tool.
Right.
Like if you are a company doing offline massive batch processing, say, you're just summarizing 1 million documents overnight, you do not care when individual tasks finish.
You just want them all done by the time you wake up.
Exactly. In that scenario, you want pure throughput, and Saga would be the wrong choice.
But for interactive agents, where a human is sitting at their desk actively waiting for an autonomous system to deploy a fix, the user doesn't really care about aggregate cluster throughput, do they?
Not at all.
They just care about their own wait time.
Precisely. You gladly sacrifice 30% of peak aggregate volume to ensure the actual user-facing tasks finish 1.6 to 3 times faster. It's really about optimizing for user latency, not just raw hardware metrics.
Yeah, that makes perfect sense. So to summarize this for you listening, I think what makes this paper so critical is that it proves the future of AI isn't just about training smarter, larger models.
Absolutely.
It's actually about fundamentally redesigning the plumbing,
Yeah.
the schedulers, the data center architectures, and the routing protocols.
We have to adapt the infrastructure.
Right. We have to stop treating AI as this series of fragmented chat queries and start treating agent workflows as cohesive, unified programs.
And I would actually leave you with a final thought to mull over based on all this.
Yeah, what's that?
If we are now building schedulers that treat AI agents like continuous running programs complete with execution graphs and speculative memory prefetching and live network migration, at what point does an AI agent stop being just a simple web service?
Oh, that's interesting.
Right. It is starting to look exactly like a native operating system process running inside the data center.
Like it's a resident program.
Exactly. Just think about the implications when these agents don't just run for a few minutes to write some code, but run autonomously for days, weeks, or even months at a time.
The scale of that is kind of mind-bending.
It really is.
And it brings us right back to our chef with the goldfish memory.
Yep.
By completely rethinking the scheduler, we've finally given the chef a notepad, a dedicated kitchen, and a sous chef who knows exactly when to hand them the frosting.
Exactly.
Now we just have to wait and see what kind of systems these agents can build when they aren't forced to relearn the recipe every 5 minutes.